When a volcano erupts, it can be explosive or effusive. In an explosive eruption, a large plume of ash may spread around the globe, disrupting air travel. And pyroclastic density currents may devastate local towns, while an effusive eruption is more localized. Volcanic eruptions are caused by rising magma. As it rises, the gases dissolved within it come out to form bubbles. As gas bubbles build, the pressure inside the volcano increases until it reaches the point where it fails, causing the volcano to erupt. Scientists have discovered there may be volcanic escape valves within a volcano that relieve the gas pressure and cause less explosive eruptions and even volcanic earthquakes. It is thought that fractures filled with ash, known as tuffisites, might be the fossil record of these volcanic valves helping to diffuse the pressure inside a volcano. Tuffisites form when high gas pressure fractures open surrounding rock, allowing the gas to escape. The gas carries ash particles into these fractures, preventing the pathway from closing by propping the fracture open. However, if the particles inside these fractures are hot enough, they can weld together, thus sealing the valve and allowing the pressure to build inside the volcano once more. By understanding how tuffisites form, we can discover if these valves act to diffuse explosive eruptions. This will help volcanologists predict how explosive a volcanic eruption will be and how far-reaching the evacuation area around the volcano needs to be.
Hello everyone, my name is Holly Unwin and I am a PhD student based at Lancaster in the BGS, supervised by this lovely team of people here. And today I'd like to talk to you about a large silicic tuffisite at Húsafell volcano in Iceland and what it tells us about the gas pressure of this volcanic conduit and how it varied through time. So I'm going to briefly outline for you how fluid pressure controls tuffisite formation, before showing you some of the structures inside the tuffisite at Húsafell and how we can use them then to estimate the gas pressure inside the volcanic conduit at the time of tuffisite formation. So in the animation we've already seen how tuffisites form, but we need a source of gas pressure to open our fractures, and that is going to come from our volcanic conduit. And as our volcanic eruption can be expected to be unsteady, we also then expect the gas pressure to vary through time. That variation in gas pressure might look something like this. And so we will have our tuffisite open once a great enough value of gas pressure is reached. And then we'll have fluid flow through that fracture, and that will be driven by the fluid pressure gradient along it. Changing that fluid pressure gradient will alter the fluid velocity, and so we can then deposit particles inside our tuffisite if the fluid pressure or the fluid velocity drops, and we can then erode those particles or transport them onwards if the fluid velocity increases again. And so in this way we can deposit different sedimentary units inside our tuffisite and also form things like sedimentary structures. And so our tuffisite then and its structures should act as a fossil record for the gas pressure in our conduit through time. And I'm going to show you the interpretations of one of these fossil pressure records. And so here is our tuffisite, the Húsafell tuffisite. And we're at Húsafell volcano in western Iceland, around 80 kilometres northeast of Reykjavik. And this volcano was active around 3 to 2.5 million years ago, with 3 phases of silicic activity separated by glacial events and mafic eruptions. We're going to talk about the third phase of this activity, or parts of it, with the emplacement of an intrusion and its associated tuffisite at around 500 metres depth. And all these features are now helpfully dissected for us here in this valley of Deildargil. If we take a closer look at our outcrop, we can see what it's made of. So we have a densely welded ignimbrite at the base, which is basically massive glass. And this really strong unit was able to stall the ascent of this silicic dike beneath. Above, we have a much more friable red ignimbrite with lots of near horizontal platy fracturing in it. And between these, we have our tuffisite, which just remains constrained to the boundary between these two units. So zooming in further, we can see that our tuffisite has a very complex internal structure. It has lots of units, and you can see these units aren't just neatly stacked on top of one another, but they're cross-cutting with lots of erosion going on as well. Zooming in again, let's have a look at our tuffisite facies. And here we've got lots of different grain sizes, as you can see, from class sort of up to 20 centimetres across, right down to tiny ash-sized particles. Most of this material has been sourced from our volcanic conduit, and so we see things like rounded pumice clasts and obsidian clasts, as well as ignimbrite clasts derived from our tuffisite walls. And the changes or the variations in these particle sizes is going to tell us about the variations in fluid velocity through our fracture with time. Now, many of these units are massive, but we also see faceted with internal structures. And so we see things like fine-grained laminations, graded beds, and also crust lamination. And these structures, or their absence, will tell us about changes in the particle concentration of our deposited fluid through time. So, thinking about a slightly larger structure for a second, here we see that our tuffisite contains many horizontal classes of ignimbrite, here coloured in dark grey in my interpretation, and these are surrounded by ribbons of tuffisite that each look themselves like a small individual tuffisite. And so it appears as though as our tuffisite was running out of space towards the end of its evolution, it was able to gain enough internal fluid pressure to break open new pathways in our sort of overlying ignimbrite roof, making itself some more space. So let's zoom all the way back out again to our tuffisite as a whole, and we can use these units then to estimate the fluid pressure that our tuffisite formed at to interpret this fossil pressure record. And so to do this, we're going to assume that we've only got elastic deformation of our tuffisite walls, and we're going to use the top equation here from Goodmanson 1983, and you can see that our fluid overpressure P needed to emplace material is going to be dependent on the length to width ratio of that unit. So if we take a whole tuffisite forming as one single pulse, 0.9 metres wide by 40 metres long, then we get an overpressure estimate of 60 megapascals. And because we're at 500 metres depth, we add 10 megapascals lithostatic pressure to that, we get a total pressure estimate of 70 megapascals. And this is crazily high for 500 metres depth. At that pressure, we could easily just fracture the surrounding rock and cause lots and lots of damage, which we don't see. And so emplacing this tuffisite then as one pulse doesn't seem to be feasible. But if we take a single unit of our tuffisite, 0.1 metres thick, an average sized unit, and assume that these are emplaced by individual fluid pulses, then we get a much lower overpressure estimate of 6 megapascals. And this is much more feasible and much closer to estimates of gas pressure at 500 metres depth that we get from conduit models. So it appears then that our tuffisite was deposited in many fluid pulses, maybe up to even 20 pulses. And it suggests that the fluid pressure of our source is repeatedly fluctuating, and so this is being driven by unsteady dynamics in our volcanic conduit. So here is a schematic to put this into context, and so we have an oscillating fluid pressure through time as recorded by our repeated erosion and deposition, and we estimated that our fluid pressure or our fluid overpressure reached a maximum of around 6 megapascals before then waning towards the end of tuffisite evolution. Another key piece of evidence come in our dome-shaped injections that we see, and these are sub-horizontal discontinuous features with a dome-shaped roof, as their name suggests. And these appear to have formed by viscously deforming the overlying material, meaning that it must have still been sufficiently hot to be able to viscously deform. And so, as these injections are just deforming the overlying material rather than opening a fracture, we don't have elastic deformation like we previously assumed. And this can allow these injections to form a much, much lower fluid pressure, potentially even less than lithostatic pressure. And so these things could then form really easily towards the end of our tuffisite evolution. Now, to form, we need to have our tuffisite being thick enough for it to be sufficiently insulated at the centre for material to be hot enough to viscously deform. And this again suggests that these injections form towards the end of tuffisite evolution with waning fluid pressure. That viscous deformation will rapidly lower the permeability of our overlying material, potentially preventing our tuffisite from growing in size, but also limiting or causing it to be self-limiting in its lifetime as a degassing pathway as well. So to summarise, we have a tuffisite with a really complex internal structure with lots and lots of units that appear to be formed by multiple fluid pulses. And these different units are recording deposition and erosion with an oscillating or caused by an oscillating fluid overpressure. And we estimated that fluid overpressure reached a maximum of around 6 megapascals before waning towards the end of tuffisite evolution. And so here we have pulsed tuffisite formation, which must have been controlled by unsteady conduit dynamics. Thank you for listening.